Study magnetic fields, magnetic force, series on electromagnetic field theory, lecture number 2.20. Magnetic fields, study magnetic fields exist in the regions surrounding DC carrying or steady current carrying conductors. These fields are capable of exerting force on moving charges. Lorentz Force Law is able to provide an expression for the force experienced by the charge when it is running in a magnetic field. In addition, this law is also able to provide an expression for the force experienced by a moving particle, charged particle, when it is running in electric field. Now, let us move further to understand various aspects pertaining to Lorentz Force Law, which gives magnetic force. Here we also consider another law, Ampere's Force Law, which also gives expression for the force that exists between two current carrying conductors. What is Lorentz Force Law? It describes the force experienced by a moving charge in a steady magnetic field. This force is called simply magnetic force because it is due to magnetic field. It is one of the two laws for magnetic. Lorentz Force Law is one. Another one is also there. It is called Ampere's Force Law. According to Lorentz Force Law, the force on a moving point charge capital Q with velocity v in a region having electric field E and magnetic field B is the phase Q into E. This part is called electric field. Another part is there Q V cross B. This part is called magnetic field. So F is written as F electrical plus F magnetic. Note here Q is the charge, point charge that is running. E is the field intensity. V is velocity. B is flux density of the magnetic field. It means you consider some stationary charge distribution. So it is giving rise to certain electric field. You also consider certain current distribution. It may be surface, it may be volume, it doesn't matter, or it may be line current. So this is charge, this is current. So current is there, so it must be giving some field intensity. Field, magnetic field. So in this region we have electric field as well as magnetic field. Now consider some particle whose charge is Q and it is moving with some velocity V. While it is moving, it experiences force. That force is given by this one. Note here B is mu into H. H is field intensity, B is magnetic flux density. The relation for point charges can be converted for line currents, surface currents and volume currents. So what does it mean? Suppose magnetic field is there. In this region, magnetic field is there. Lorentz Force Law as it is, it gives an expression for force experienced by a charge. Suppose a point charge Q is there, it is moving with certain velocity. Force is given by Lorentz Force Law. Now, if we bring a line charge, another line current into the field, or a conductor carrying filamentary conductor, if you bring, this fellow experiences certain amount of force. Or if you bring a surface charge into this region, it experiences some force. If we bring some volume current, this also experiences force. I repeat, Lorentz Force Law as it is gives the force experienced by a moving point charge. This expression, however, can be extended to the force experienced by a filamentary current, surface current, and also volume current. How it is extended? Consider current. By definition, current is dq by dt. dq by dt can be written as dq by dl, dl by dt. But dl by dt is velocity. Now you use this relation. One can use this relation to replace velocity and the charge. We can replace. Once we replace, we will be getting like this. Magnetic force is I dl cross B. This is differential length B. Similarly, of course, there is an equivalence between current elements. I dl equal to kdA, which is equal to J d tau. From that equivalence of current elements. From that equivalence, one can simply move towards F magnetic field. F magnetic force is K into dA cross B. J cross B d tau per volume current. That is so far as Lorentz Force Law is concerned. Now, as already mentioned, there is another law which also describes magnetic force. But here, the magnetic force is the one that exists between two current carrying conductors. Okay. Again, here two parts are there in this law. One for current elements, another for current loops. First, we consider the part that is related to current elements. According to this law, the force between two current elements and different current loops is directly proportional to product of current elements, inversely proportional to square of the distance between the current elements, directed normal to both the current elements as well as vector joining the elements. What he is trying to tell is, you consider some current loop, current carrying loop. You call it I1, current is I1, loop C1, another current loop. Call it C2, name it as C2, and let us say current is I2 here. Now, if you consider differential length, let us call it DL1 here. Because it is over C1, you can consider another differential length here. Call it DL2 because it is over C2. Now, the point is this, I1 DL1 is current element. The current in DL1 or current element I1 DL1, it is a source. According to Biot-Savart law, it creates magnetic field. So, everywhere you have magnetic field. Everywhere magnetic field is there. This magnetic field is created by I1 DL1. Now consider DL2, current is I2 in this loop. So current element here is I2 DL2. As I2 DL2 is in the field created by I1 DL1, it experiences certain amount of force. What is that force? That force is given by Ampere's force law for current elements. Now, another part of this law is there that gives you force experienced or force that exists between two current loops. Now, so far we considered field given by I1 DL1. If we consider entire length of C1, then it gives rise, entire length gives rise to certain more amount of field in this region. Naturally, because I1 DL1 is small or DL1 is small, if you consider the entire loop, naturally, or we can expect, we can assume that the field given by the entire C1 is going to be very large. Therefore, the force that exists between I2, DL2 and C1, we can expect that it to be very large when compared to the force that exists between I1, DL1 and I2, DL2. If we want force experienced or force that exists between C1 and C2, then what we have to do is, first we have to compute the field due to the entire loop C1 and the total force experienced by the entire loop C2. How it is done? First, we integrate over C1 to find field intensity created by it, and then we have to integrate over C2 to get the total force that exists between the two loops. The expression for this force is given by Ampere's force law for loops. So these three statements, they pertain to current element. And if you perform double integration over the force that exists between current elements, naturally we will be getting force that exists between the current loops. Here is shown, one is C1, here is C2, current is I1, current is I2, everything is as already explained. So further explanation is not required. According to this law, mathematically the force on a current element I1 DL1 due to current element I2 D2 when both are arbitrarily oriented can be expressed in this. Here medium is assumed to have a permeability of mu. Note that for general case of arbitrary orientation of current elements DL1 and DL2, the forces on them dF1, dF2, dF12, dF21, they are not equal and opposite. This is not considered as violation of Newton's third law, since isolated current elements do not exist in reality in any way. For current loops, in case of, if you want to know force that exists between current loops, as already mentioned, we have seen integration has to be performed twice. Once over C1, another time over C2. Now, the resultant expression becomes this one. F1 to A is mu I1 I2 by 4 pi. This is integral twice dl1 cross dl2 cross r cap by r square. Inner integral gives field produced by the entire loop C2, whereas outer integral gives total force on C1 due to the field C2, loop C1 due to field of C2. Here, it is required to be mentioned before going further. The fact is, Ampere's force law, it can be easily derived within no time from Lorentz Force Law with the help of or taking help from Biot-Savart law. In other words, Lorentz Force Law combined with Biot-Savart law is able to provide Ampere's force law. Before closing, let us recollect as it is. Lorentz Force Law gives force on a moving point charge when it is in magnetic field. Ampere's force law has two parts. First part gives force that exists between two current elements. Second part gives the force that exists between two current loops. An alternative expression is also available for the force that exists between two current loops. Here it is shown. F12 is minus mu I1 I2 by 4 pi. Two line integrals r cap dl1 dot dl2 by r square. The forces on two individual current elements may not necessarily satisfy Newton's third law, but on loops it is always satisfied. Here a comparison between magnetic force and electric force is given. Expression for magnetic force is QV cross B. It is QE in case of electric force. It acts upon moving charged particles. It acts both on moving as well as stationary. Magnitude is proportional to particle speed and direction is normal to particle velocity. But electric force is independent of velocity. It is always perpendicular to direction of field. Magnetic force, but it is always parallel. These forces do no work, whereas these forces do work. Speed of the particle remains constant under the influence of magnetic fields. Total energy remains constant under the influence of electric fields. Then we come to an end to the present session. Enough for now.